Okay, this is going to be a specific example of the idea of using a calorimeter to find the change in chemical energy of the reactants, or I've been calling it the change of chemical reaction all the way through this, but really the proper term for this is enthalpy. So when I say that delta H thing, the word I should be using regularly is enthalpy. So I have 2 grams of potassium nitrate, KNO3, and we're putting into a calorimeter containing 200 milliliters of water. Temperature of the water is going to decrease from 24 degrees Celsius to 21.8 degrees Celsius. Determine the chemical energy change, or as I said, enthalpy, for the salt dissolving in the water. So it's going to break into the ions, and there's going to be some energy either going in or coming out of this reaction. So first of all, let's write out some of our given pieces of information here. We have a temperature 1 of 24 degrees, a temperature 2 of 21.8 degrees. Both of those are Celsius. We have a mass. It says 200 milliliters of water, but we remember that property of water, that 1 milliliter is the same as 1 gram. So that really means 200 grams of water. We have a specific heat capacity of 4.18 joules per kilogram or per gram degree C. So with that in hand, we can use all of those things to figure out the energy associated with this temperature change. Q is equal to mc delta T. So let's just do delta T first. T2 minus T1, 21.8 degrees C minus 24 degrees C, negative 2.2 degrees C. So 200 grams, 4.18 joules per gram degree C. Delta T, negative 2.2 degrees C. So 200 times 4.18 times 2.2, I get 1,839.2, and that's all negative joules. So I know I have 2 grams of the potassium nitrate. I'd like to find out what the general delta H is, the amount of energy per mole. So I'm going to assume that my calorimeter is a perfect closed system, an isolated system, and I'm going to say that E is going to be equal to negative Q. So the energy lost by the surroundings will be gained by the chemical reactants here. So E, remember, the energy is associated with 2 things, the number of moles and the amount of energy per mole. So moles times delta H is going to be equal to negative Q. Hold on a second here. We need to figure out what our actual number of moles is. We have a mass of 2 grams, and we have a compound, potassium nitrate, so we can get the molar mass of that compound. Potassium is 39.1 grams per mole. Nitrogen is 14 grams per mole. And oxygen is 16 grams per mole. So the molar mass here is 101.1 grams per mole. So moles are equal to mass divided by molar mass. 2 grams divided by 101.1 grams per mole. And I get 0.0198 moles. So 0.0198 moles delta H equals negative Q. So Q is this. So 2 negatives are going to make this positive, 1,839.2 joules. So again, there was a negative here, there was a negative here. I said two negatives make a positive, and that's why I've put this number in as a positive. So I can get my delta H now. 1839.2 divided by that gets me 92972 joules per mole. So most of these guys are stated in kilojoules per mole, so this would be 92.972 kilojoules per mole. You'll note that it's positive, so this is an endothermic reaction. If KNO3 was here, breaking that ionic attraction is going to cost more energy than hydrating the K plus and the NO3 minus. So K plus and NO3 minus aqueous are up here. So this is actually going to increase in energy. That energy has to come from somewhere. That's why the temperature of the surroundings went down, because that's what paid for the energy to dissolve this salt. So that is how you can find delta H using a change in temperature from a calorimeter with a known mass and a known substance.